A warm welcome to the presentation of real-time pose estimation for traffic vehicles. Our project focuses on integrating the task of object detection, particularly for traffic vehicles, with the pose estimation for said objects. Previous work in this field include the EgoNet 2021 methodology, which implements and demonstrates the importance of intermediate geometrical representation for pose estimation. Inspired from this technique, we make an attempt to calculate the pose of vehicles using monocular images from the Kitty dataset. In addition to this, our objective is also to develop a model which is robust enough towards diverse and biased dataset, which outputs fruitful results in real time. In addition to this, our work is also inspired by the ResNet model. We divide the project tasks into two separate pipelines. The first one handles the object detection task where we implement YOLO V7 model using its pre-trained weights. This step allows us to feed input images from the Kitty dataset, which outputs the classification as well as LTRB bounding box details of the vehicles. The image is then cropped for each bounding box and resized to a 128 x 128 dimensional standard output, serving as an input for the next pipeline. Pipeline 2 covers the pose estimation part. The input is the cropped image along with their pose information, as shown in the figure on the bottom right. For simplicity, we consider a two-dimensional pose of the object drawn in the image plane.
To train our pose estimation model, we use the Kitty dataset, which has over 7,000 images with their corresponding ground truth labels. These labels include the bounding boxes around the detected vehicles as well as their pose. However, as seen in the figure to the right, the dataset is very biased towards two poses, with one being cars facing directly away from the driver and one being cars directly facing towards the driver. This causes a major issue for training our model with this dataset, as the biased dataset can lead to overfitting towards certain poses that are more frequent than others. Our solution to this problem is to have our pose estimation model not map to all 360 degrees of the poses, but instead to 14 bins, each bin being a range of poses. This ensures that the model has enough variety for every single bin to be properly trained on all the different poses it can see. Along with this, during training of the model, we use 14 different data loaders, each one specific to a bin. And those data loaders feed in an equal representation of each bin during the training process to ensure that the bias does not carry over to the training and the model does not overfit to certain poses. The dataset also includes some poor images, which we were able to eliminate through filtering using the image height to width ratio, as well as removing any image which has a low number of key points found through the SIFT algorithm.
The object detector we implemented is the new YOLO V7. It was authored by Wong-Kin Yu and Alexei Boshkovsky. They created a network architecture that would predict bounding boxes more accurately than its peers at similar inference speeds.
The following ResNet block is used in our network architecture to leverage its benefits. It is a series of convolutions and batch normalizations, and then a summation with the original inputs. We also include in our network architecture this EgoNet block, which was inspired by the EgoNet paper. This includes convolutions at 3 different layers, each being a different downsampled version of the input image. And at the end of the block, the output of these 3 layers are summed together. And this is the network architecture for the fast pose model, which does the pose estimation. It is fed a 128 by 128 input image of a vehicle and includes a series of convolutions, ResNet blocks, EgoNet blocks, where that output is flattened and is fed into 2 fully connected layers. And the end result is mapped to the 14 bins. The softmax of this output is taken, and the highest value is what the model outputs as the pose of the input vehicle. As seen in the results, after training, this model yielded very high accuracy. The metric we used is K-accuracy, where if the output bin correctly matches to the label bin or is directly next to the labeled bin. Here we can see the result performed in real time. First, the object detection of the vehicles, and then those patches are fed into the pose estimation model, where the pose is directly printed onto the vehicle, up meaning the vehicle is going away from us, and down meaning the vehicle is coming toward us. The goal of our research was to bring together state-of-the-art implementations and approaches to tackling the robot driver problem. And we believe we successfully did this by creating our own model for pose estimation that is influenced by EgoNet, ResNet, as well as our own concoction. We took many measures to ensure that our model is accurate and not susceptible to the biased dataset. Thank you for listening to our presentation.